So let me start from here. So for those who don't know me, that's me. And I'll be talking about a paper which came out just last Monday on ECCC. This is the paper called Arithmetic Circuits. Chasm at depth 3. And this depth 3 is what is, so there were lots of papers with this title or similar titles with depth 4 earlier on, and this is it's a surprising, I think this surprised everybody that something like this is true even for depth 3. This was not believed to be true, the result of this paper. The authors are Gupta, who was here for a little while, Kamath, Neeraj, and Ram Prasad Saptharishi. Yes, so the paper is called, I think. Okay, so let me state the main result, which is good. So what they show is over the rational, so this works specifically over the rational numbers. It's not true over small finite fields. So over the rationals, if you have a f which is an n-variate degree d polynomial, and if you know that f has arithmetic circuits of size C computing it, circuits of size S, maybe size S, which compute it, then they show that this implies that f has depth 3 circuits. So it is called the class of depth 3 circuits. They use the 3 layers of gates, some gates, then there's a layer of product gates, and then there's a layer of sum gates. So it has sum product sum circuits of size significantly smaller than what was expected. So this is exponential in O of square root of d times some polylog factors. So there's log n, log s, and there's a log d also. So start with any arithmetic circuit of size s computing a polynomial. It can be basically squashed down to a depth 3 circuit of this size. So let's assume that for now that s is polynomial in n. So d, s, n, they're all polynomially related. So this is just a polylog factor. So you can forget about that for now. What's surprising is that the size is something like 2 to the order square root d, where what was probably previously expected is something like 2 to the order d. So this square root is very surprising. And a very similar result was known prior to this work for depth 4 circuits with a similar exponential blow up. So with very, very similar parameters, it was known for depth 4 circuits. This is a result just from maybe a year ago. And I'll say what this is, but the paper strengthens it over the rationals to depth 3 circuits. So this is also over the rationals. Good. So the degree is also going to blow up. So the degree is roughly the same. the formal degree. So it's going to compute, so here you have a polynomial of degree d, which might be something like n. But here you'll have circuits of computing intermediate polynomials of degree as large as the size roughly, and then they'll all cancel out to eventually compute the same polynomial. So the degree is going to be huge. So the current paper which is out on ECCC shows that when that paper had the reduction starts with a circuit over rationals and then produces a depth 3 circuit over the complex numbers. But so there's been a revision since then. I don't know if it's up on ECCC yet, but when the authors learned that I was giving the talk, they sent me the paper where they can now get this circuit over the rationals too. So you start with the circuit over the rationals, you maintain a circuit over the rationals.
You're giving another talk next week.
The depth 4 results worked over manifold?
Yeah, depth 4 didn't use. Depth 4 works over all fields. Yeah, the depth 4 is much more just a cut and paste. You start with the original circuit. It's more cut and paste feeling than the kind of transformations which go on inside this, which are field specific. Okay, so.
The depth 4 was really a variant of the variant Stuhm-Berkowitz of reduction of depth. So there the reduction doesn't pay in size, it's take a longer size and it becomes like log depth. And it's a variant of that where you squash it more and you pay more in the size. But it's clear what the trade-off is more or less. The variant Stuhm-Berkowitz and Rakov could have done the depth 4 result if they thought about it.
And so the depth 4 is not, so it will be an ingredient here. We'll first squish it to depth 4. I'll just say a few words about how depth 4 happens. It's not that hard. And then we'll see what this goes. Okay, so but an interesting consequence. So let's see what are the consequences of having this result. So one is that, okay, to show lower bounds for general circuits, it suffices to show strong enough lower bounds for depth 3 circuits. Okay, so I'll tell you what is known for lower bounds for depth 3 circuits already. But so that's an immediate consequence, that to show lower bounds, it suffices to show lower bounds for depth 3 circuits. But another surprising consequence is that now this gives us sub-exponential size depth 3 circuits computing the determinant, which was not known before. So we have polynomial size arithmetic circuits computing the determinant. It was not believed that there were sub-exponential size depth 3 circuits computing the determinant. But in particular, this gives us a way of doing that. So there exists a sum product sum circuit of size exponential in of root d log d. Computing a
Even the d was not known, only
even
d factorial.
Even d factorial. The only bound known thus far was d factorial, which is the trivial monomial expansion of the determinant. So the trivial monomial expansion is a sum of product, is a sum of products. So it is a depth 3 circuit, and that is d factorial. The size of that circuit would be d factorial. Okay, so this is the first non-trivial depth 3 representation of the determinant. I wrote here square root of d log d, so I'm fudging in some log. So they show that if you have arithmetic circuits of size s, then you have sigma pi sigma circuits of this size. If you knew branching program lower bounds, and I'll define what this is. Upper bounds, yes. So if you knew that f has branching programs. So a branching program is more restricted than a circuit. It's a slightly more restricted model of computation than a circuit. And if you knew that f has a branching program of size s, then they showed that you can get rid of this log d factor, would not be there in that case. You can see you can gain a little bit.
Still, wouldn't give d log squared?
Well, it's outside the square root.
Oh, right.
Right. Okay, so branching programs and arithmetic circuits are given an arithmetic circuit of size s, you can get an equivalent branching program of size something like s to the log d. So just by the transformation between arithmetic circuits and branching programs, it just plugs into these bounds and everything follows. Okay, so one consequence is that you get sub-exponential size circuits for the determinant. Another consequence is for the problem of polynomial identity testing. So plugging into earlier results for which relate lower bounds to polynomial identity testing, this says that if you can do PIT for depth 3 circuits in polynomial time, then this implies quasi-polynomial time PIT for general circuits. Black box. Okay. So that doesn't work for white box, that's true. So in the black box setting, implies something like 2 to the I think the degree of the polynomial d needs to be related polynomial to n for this result to go through. For general circuits of okay, so for the last few years, everybody was going around saying that, oh, if you can do this, do PIT for depth 4 circuits, it implies PIT for general circuits in quasi-poly time. But now suddenly you can say this about depth 3 circuits too, which is, I guess, very unexpected. So let me tell you what the state of affairs was before this paper. To the log n, 2 to the polylog n. I think this is for exactly the same reason why for depth 4 circuits it held.
No, but for depth 4 circuits, it's only because the circuits are homogeneous, and here it's not homogeneous. It doesn't change it.
I don't think it changes anything. Yeah, I don't know if the homogeneity got used in that result anyway. Just the size, I think. Yeah.
I don't know the depth 4, so can you say a few words on why the PIT is indeed quasi-polynomial and not
You're not polynomial?
no, it's not exponential, not sub-exponential.
You have this exponential block in the circuit size, but that's
Oh, I know. I can tell you why. If you prove, okay, so good. So, okay, good. So to prove so all this result says is that to prove a super polynomial lower bound on the permanent, it suffices to prove a super 2 to the square root d lower bound for depth 3 circuit. But if you prove a much stronger lower bound for depth 3 circuits, if you prove 2 to the n, yeah, if you prove 2 to the n to the 1 minus epsilon, or a 2 to the n lower bound for the determinant, not for the determinant now, but if you prove a 2 to the n lower bound for the permanent, then this would imply an exponential lower bound for general circuits. So polynomial size circuits became 2 to the root d, but 2 to the root n size circuits, it would prove a lower bound of the form 2 to the root n for general circuits. So you can see how large you need to make S here for this still to be meaningful. So
calculation, but it's just you need for the de-randomization. The PIT requires you want exponential or sub-exponential lower bounds than that.
Okay, so the PIT won't work by taking a circuit, applying this transformation, and then applying the
Absolutely.
PIT. Oh,
Yeah, it will. But it's the sizes will be different. You will not start from polynomial to 2 to the root n. You will start from exponential to a sub-exponential. And the relationship will be exactly between
oh, I see.
poly and quasi-poly.
Right, so if you just get a sub-exponential de-randomization of black PIT for depth 3 circuits, that will give nothing.
It will give
Yeah,
nothing, I think. It will give
probably
nothing.
will give nothing, yeah.
Yeah.
But this was the same with depth 4.
Yeah.
Yeah.
Okay, so
Just out of curiosity, is there like do they give a depth size trade-off? Like if for determinant, say, if I allow you depth r.
so it's already known that the determinant can be computed in log depth with poly size.
Yeah, let's suppose I give you 10 layers or log layers or something. I mean, is there
So I don't know if this paper gives it, but I think the earlier papers, so I don't know what the precise trade-offs are, but I think a lot of techniques would give you a smooth way to go, but I don't know what the exact bounds are. It would still be, for any constant depth, it would still be some 2 to the n to the epsilon,
I don't think that
is
it
my guess.
matters if you allow the depth to go higher, because this Agarwal Vinay, I mean, what depth 4 without, actually it's not just a depth 4 without, I mean, this technique of Valiant Skimberkowitz and Rakov that gives depth reduction would give you, if you want depth 6, then you get 2 to the n to the third. You want depth 8, it would be 2 to the n to the fourth. And there the distinction between 4 and 3 sort of disappears. So they don't, I mean, the edge in their new result is that you can make the 4 a 3.
I mean, I understand that this is the 3 is really the.
No, so I'm saying for other results, you already had them.
Oh, okay.
You had them. So you have the trade. There is a smooth trade-off.
Oh, okay.
There is a smooth trade-off. People didn't concentrate on it, but there is a smooth trade-off. Just roughly what I said. You want that D, and you get 2 to the n to the 1 over D, roughly. So if you are really picky and want D minus 1, then maybe you can. Maybe this will get, but here, nobody could go below 4.
So let me tell you why. So why 4 is important. Okay, so why we thought 4, why people thought that 4 was the limit of this technique is what was known in the past. So Nissan and Wigderson in 97. So first they showed that so notice that, so this general depth circuit got squished to a depth 3 circuit, but the formal degrees of these circuits are really, really high. And in some sense, that blow up in the degree is necessary to have such a transformation, because this paper shows that over all fields, in particular even the rationals, that so any homogeneous sigma pi sigma circuit computing this d by d determinant must have size exponential. Okay, so homogeneous is not is not as hard a restriction. So you don't if to compute the d by d determinant, if you want the degrees of this circuit to be at most 10 times d or some linear function times d, then you can prove a fully exponential bound, lower bound on the size of the determinant. So you would need these huge cancellations if there's any hope of squishing the determinant down to a small circuit. Another result worth taking note of here is by Grigoriev and Karpinski in 98. And they showed that, okay, even if you drop this condition of homogeneity, but if you want the computation to happen over small fields, small finite fields, then it cannot be done. So they give an exponential 2 to the d lower bound for computing the determinant over any small finite field. So arithmetic circuit over a fixed finite field. And computing the determinant. This again must be of size
So we cannot hope to extend it. So
yes, so this result is not true over say f2 or f3.
It is over large enough.
Maybe large enough if
Well, large,
right. So if you Right. So when we see the proof, we can see how far it can be extended. So I think if the characteristic is large, and the size is much larger, something like 2 to the root n, then maybe everything goes through. Characteristic needs to be growing as a function of n. So characteristic needs to be, I think, at least something like d, where d is the degree of the polynomial, before anything kicks in. So I think this result would hold for large characteristic, and the field size also needs to be something like 2 to the root d. But if you have any fixed field of small characteristic, then this result, for instance, says that you cannot write the determinant as a small depth 3 circuit.
If the limit over the rationals, do you have a bound on this block in the size of the coefficients that you get? So like also 2 to the root d? I think so.
Probably. So there's a big there's probably some big Van on the matrix you need to invert somewhere. 2 to the root d by 2 to the root d Van on the matrix with distinct entries you need to invert, and that will show up in the coefficients. So I am whatever blob. So there must be pretty big coefficients. Okay, so that's for these circuits. Okay, good. Right. So both these results somehow, because of these two results, people didn't believe that this, or even expect that such a result would be true over the rationals, why the rationals would behave differently. And so we seem to have, a lot of fields seem to have optimal lower bounds for depth 3 circuits. And so it just seemed like, depth 4 circuits were what were not understood, but if you understood depth 4 circuits well enough, then this would give general lower bounds. But at least over now, the rationals, it seems that depth 3 is where, which is what is pretty interesting. Though it's not, actually, for depth 4 circuits, when it sufficed to prove lower bounds for depth 4 circuits to prove lower bounds for general circuits, there was no degree blow up. So a degree D general circuit got reduced to a degree D depth 4 circuit of a suitable size. So this in the depth 4 reduction, there was no loss of homogeneity. So it still might be possible that it's easier to work with depth 4 circuits than to work with these depth 3 circuits with huge blow-ups in degree.
The best lower bounds for homogeneous degree depth 4 are exponential, and the best lower bounds for non-homogeneous depth 3 are
right. Good.
quadratic.
Right. So because so I'll mention what it is. So we already know exponential lower bounds for certain certain interesting classes of depth 4 circuits. But for non-homogeneous depth 3 circuits over the rationals, which is what we need to look at in case of this reduction, the lower bounds are much weaker than what's known before. So the best bound we know, so is just a quadratic lower bound. So I think for the d by d determinant, so there are d square variables here, the lower bound is something like d to the 4. So something like roughly a d to the 4 lower bound, and this is by Spilka and Avi.
This is also for it's actually a symmetric function.
It's so this holds also.
It's really for formulas examples. Well, okay, it's for them. It's a little. No, we are counting wires at the bottom. So The number of product gates is linear. yeah, the number of product gates. Each one has degree.
So we're probably even weaker than what I state here. Yeah, so the best lower bound, so it's for the determinant also holds for the symmetric function, but it's much, much weaker. So the gap between what bound you need to show for these depth 3 circuits in order to imply a result for general circuits versus what is known, there's a huge gap. right? So the quadratic versus 2 to the root d. But in contrast, for the multilinear case, we know exponential lower bounds, right?
The depth for reduction works for multilinear case as well. Does this not work?
No, so here you lose multilinearity. So I think you start with general if you start with general multilinear circuits, depth 4 it stays multilinear, but after that there's no multilinearity anymore.
No, but even then the variance considered the Berkowitz-Markov and the other one Binet lose multilinearity. Multilinearity you lose immediately if you do depth reduction. People don't believe that you can do depth reduction and do the multilinearity.
Otherwise, then you can carry on
Yeah.
multilinearity
No.
with respect to lower bounds.
But I don't think so.
Not from circuits to formula. Maybe if you start with a formula.
Maybe for formula. I mean, reduction from circuits to formulas. That's what I'm looking for. People don't believe, and probably false. Nobody has a polynomial time multilinear algorithm for determinant. Polynomial time multilinear. People believe that could be exponential.
Okay, anyway, so here, so at least for what is known and what you need to show that there's this huge gap. Let me say something about the gap for what we know in depth 4 circuits. Okay, so the earliest paper probably on depth, one of the earlier papers on depth reduction was this paper by Valiant, Skyam, Berkowitz and Rakov from 83, where they showed that any arithmetic circuit can be shrunk to a circuit of size of depth something like log square in the parameters. So if f is a polynomial, they showed of degree d, and it's computed by an arithmetic circuit of size s, then you can replace it by an arithmetic circuit of size which blows up just by a polynomial, but the depth is something like log s times log d. So then depth order log s times log d, and the size is something polynomial in s.
I would say it's not one of the other. I mean, this breakthrough paper that shows that in the arithmetic world, P equals MC, which we don't believe in the Boolean case. So they really exhibited in the strongest possible way the distinction between the two and why maybe arithmetic circuit lower bound would be easier than this.
Right, so there you go. So this is already the first very surprising result, and so the depth already reduced a lot. And now, then there was a sequence of papers. First one by Agarwal Vinay, and then by Koiran, which basically started from this result and strengthened it. It's not, so if we have time, I'll talk about this, how you go about doing this strengthening. It's not too hard. Where you can further squash the depth down to depth 4 circuits, but then there'll be a blow up in the size where s will go maybe to something like 2 to the root s or something like that. So let me state what that result is. So Agarwal Vinay in 2008 and Koiran is just 2012. What they showed is the following. So if f has circuits of size s, and at least for the Koiran result, let's assume that s is, this is not necessarily, let's assume that the size is polynomial in the degree for now. Then f can be computed by depth 4 circuits of size 2 to the order something like root d log square d. Okay, so very similar blow up in the size, but they get it for depth 4 circuits. So let me say if f is circuit size, if f is homogeneous, then these depth 4 circuits are also homogeneous. This is very important. Then f can be computed by a depth 4 circuit of size something like 2 to the square root d, but these depth 4 circuits are homogeneous. And this is quite a powerful feature of this reduction, that it preserves the formal degree of the polynomials when you do this squashing operation. What they also, these sequence of results also gave some additional structure on these depth 4 circuits. They're not just any depth 4 circuits of big size, but so these depth 4 circuits are, so there are 4 layers. There's a sum, then there's product, then there's sum, then there's product. Right? There's 4 layers of gates. Suppose this is computing a polynomial of degree d. So then they are able to make it such that both these product gates individually have fan in square root d. So you can ensure that up to this point, all the polynomials computed are of degree square root d, and then these product gates take in square root d polynomials of square root d to get total polynomials of degree d, and then you sum such polynomials. So they got this additional structure, and they showed that these circuits are of size at most 2 to the root d. So in particular, if you want to show, using this reduction, if you want to show lower bounds, you want to get super polynomial lower bounds for the permanent for general circuits, then you need to prove that depth 4 circuits of this form need size at least little omega of this, right? And so that's what we need to show. And what was, so just a few months ago, by the same set of authors, there was a paper which showed lower bounds which come really, really close to this particular bound, which you need to beat to prove lower bounds for general circuits. So I can maybe just say the same set of authors, that's G, I think it's GKKS, 2012. They give 2 to the omega root d lower bound for the permanent of size d, which we want to compute it by these depth 4 circuits with root d. So by exactly this class of circuits, if you want to compute the d by d permanent, they show that that circuit needs to be of size at least 2 to the root d.
And the lower bound works for determinants as well.
The lower bound, so let me get to that. But so there's only a log square gap in the exponent. This upper bound and lower bound seem to come really, really close. And so if you just basically gain 2 log square factors in the exponent here, it seems that you would prove lower bounds for all circuits. So either if you improve the lower bound even slightly, or this upper bound here even slightly, it seems that you would have some pretty drastic consequences for general circuits. So as Avi pointed out, so what they also show is that this 2 to the root d lower bound for the permanent also works for the determinant. So I don't know if they do it. In the paper they don't do it, maybe the calculation goes through, but it's a tough calculation. I mean, it's a very delicate calculation. I'm not sure if it goes through. Okay, so the fact that it works also for the determinant seems to say that since the proof technique which works for the permanent also works for the determinant, and you know that the determinant can be computed by polynomial-sized arithmetic circuits. It seems that just working a little bit harder might not give you exponential lower bounds for the permanent by just improving it slightly. So any proof technique which will allow you to prove lower bounds for general circuits must distinguish between the permanent and the determinant, because we know that the determinant already has polynomial-sized arithmetic circuits. We believe the permanent doesn't. And
without getting into technical details, they do know specific features that make the determinant result tight and the permanent result probably not tight. I mean, they are using some complexity measure which is known to be exactly sharp for determinant and probably is far from being sharp for permanent. So it's possible that you could distinguish them.
right, so it's possible. So they have a complexity measure which at the moment they don't know distinguishes the determinant and the permanent. It's believed to be tight for the determinant, may not be tight for the permanent, but I think that even if it is not tight for the permanent, they might shave off one log factor in the exponent, which still wouldn't get you lower bounds for general circuits. It wouldn't get you 2 log factors, just 1. Okay, so this depth, in that sense, this depth 4 reduction, because the lower bounds and upper bounds are so close to each other, this seems the more, I don't know, the more scary regime where you don't know which way it's going to go, what's going to happen, what it would take to overcome this barrier. Here you've got down to depth 3 circuits, but still the upper bounds and lower bounds are way off. And the reason for that is, the main reason is that these circuits are non-homogeneous. So the lower bounds which worked, these lower bounds which worked for depth 4 circuits don't work for those depth 3 circuits because they're not homogeneous. Okay, so I think, so that's basically the state of affairs. So now let me talk about what ingredients go into this this depth reduction to depth 3 circuits. Okay, so we'll start with this result, which is a reduction to depth 4 circuits. Maybe I can even say a few words about how this reduction works. So I'll start from this VSBR paper, which shrinks it down to log square depth, and then the reduction to depth 4 circuits of this form is not very hard from that. Valiant.
Valiant, Scume, Berkowitz, and Rakov.
Who's Q? Is he around?
Scume is yeah,
I
it's
don't-
Denmark, yeah. It's,
Okay, never met.
some fancy people.
Okay.
In Aarhus, yeah. He was
Okay.
a student of Valiant. They wrote together several papers at the time, the original VP-VNP complexity theory based on linear algebra, some really cool papers.
Okay, so let me give you a very high-level outline of, so a sketch of what are the ingredients which go into this reduction. Okay, so we start from this circuit C, which is a general.
Just one more word, since you asked about Scume and Rakov, I'm sure everybody knows, but Berkowitz was the first person to give a depth reduction. He was the person who proved that determinant is in NC, has a polynomial size, depth, log squared, and arithmetic circuit. He was a Berkeley student, and he improved a result of another Berkeley student, Iafi, who just got the depth to log squared, but the size was into log n. So I guess he was the original depth reducer.
Okay, so here's the outline of how the steps in the proof. So we'll start with the general circuit C, computing some polynomial f, and then we'll depth. So this the two-step depth reduction. One is by this VSBR, which will take it to circuit of depth something like log s times log d, without too much of a blow up in the size. So it's just a polynomial blow up in the size. From here, we get a depth 4. So something like so if you make the degree here A, the degree here will be something like D over A. So they'll choose these A and D over A carefully just to fit all their parameters.
Just to get the right
Log
right
factor.
but,
So for now, let's say.
basic would be,
So yeah, so basically root D. Okay, so if this circuit was homogeneous, so if this was homogeneous of degree D, then this is still homogeneous, and this is still homogeneous of degree D. And but the size blow up, so these circuits are now much bigger. So this size here is something like roughly 2 to the root D with these but there might be some log square factors I'm hiding. Okay, and this is Agarwal, Vinay, and Koiran. Okay. Now what they do is they start with these depth 4 circuits, these special depth 4 circuits, and they convert it to depth 5 circuits, but of a very special form.
so that's the new paper now.
This is the new paper. So the current paper, what they do is start with these circuits and compute it to depth 5 circuits of the following form. So what are these? So instead of product gates in this circuit, they have powering gates. And so a product gate takes in a lot of inputs and multiplies them. A powering gate will just take in the same input and raise it to some power. So you can think of it to be a product gate taking the same input many times. So these are powering gates. And I think the same root D. It's still homogeneous. And if this was 2 to the root D, here the size is still roughly. So now this is 2 to the root D. Yeah?
So is this the first time that the powering gates are actually used in these circuits? Reduction?
No.
So they've been used. So I don't know if they've been used in the context of depth reduction, but they've been used. So here's the component which allows them to go from here to here. So they cite Fisher's identity. So this is I'll talk about this, but it's been used elsewhere too. So recently I saw, so Amish Pilka had a paper on symmetric polynomials so long ago, which uses exactly this transformation, which takes in a product gate and converts it to this powering gate. So I'll mention what this is. But this transformation was something not used in this context before, but it seems to be well known. So this is quite an easy transformation.
All the people studied the low bounds for representation by sum of powers, like Niraj.
Yeah. So this was So this is so what the result is this. To go from here to here, what you're doing is you're taking any product gate or say any monomial which just multiplies a lot of variables together and converts it to a sum of powers of linear functions in these xi's. So x1 through xn. So x1 up to xn with a transformation which takes it to a sum of li to the n, I going from 1 to 2 to the n. So every product of n things, you can find linear functions in these variables and raise them to the power n, take roughly 2 to the n of them and sum it up and get an identity. So that's,
No.
this is not duality, this is more something like inclusion, exclusion. The duality is the next step, the Saxena's duality thing. Here this is just a simple identity which will just replace x1 to xn by this. You just plug it in. For every product gate which appears in the circuit, you transform it to a sum of powers, and this will transform the circuit to something like that.
Why is the VSBR result required here?
No, so VSBR, so you can just say, I can call this Agarwal Vinay. It's not required, but the one component in the Agarwal Vinay result was VSBR. Right. Okay, so and now once this depth 5 circuit, once you have this depth 5 circuit with these powering gates, there's just one more component which will take this and squash it down to a sum product sum circuit. And here is again the tool they use is an identity by Saxena from 08. This is what Ilya called the duality. So this is so again it's just a piece. So it's a transformation which takes in a powering gate and replaces it with a sum of products of variable disjoint polynomials. So it's yeah.
I'm pretty sure this trick was in the paper of Avi and Amir's
It's not exactly the same. I looked after you said. We use a similar, it's not this.
Remember Amir showing me this and telling me it's from the paper.
Yeah, so yeah, so maybe he showed you something different, or he knew this also, which is quite likely, right? Because yeah, I looked at the paper. It's actually in the same paper, and it proved the law bound that you raised.
So even last night, even I was looking at the paper to see. Even I thought I saw this, but then I couldn't find it precisely.
We use a similar. It's not this duality. There's some related identity. They all emanate somehow from the Newton identity.
There's this identity here which you can just plug in out here and immediately. So there's not much hard work. You just do the computation and you get this circuit. But at least for me, even if you see this circuit and you know the duality trick, it's not obvious that it will help, because there are these two layers of power gates, and they all nicely collapse somehow when you use it on both. If you just had a power sum, you wouldn't even think of using the duality. It's just complicating the circuit more in some sense. So just knowing the duality trick and you coming this far, it's not obvious that you should apply the duality trick to this, and it will all cancel out. So, yeah.
Duality trick here, does it refer to conversion of symmetric polynomials into...
So let me state what the duality trick is fully. Okay, so what the duality trick is doing is, let's start with just some linear form.
Don't want more space to run. You don't suppose it's bigger.
Okay, so what was this Saxena's thing? The identity is the following. You just take lots of, say, disjoint. So you have some linear form, which is, so you have some power of a linear form, right? Because here you're seeing powers of things. So you take a power of a linear form, then it can be expressed as a sum, I going from 1 to, so m was the number of variables, d was the degree, of some constants times a product of univariate polynomials in the UIs. Okay, so I'm putting in more notation than I need. So there exist these constants alpha i's and beta i's. The E is just it's some univariate polynomial I'll specify, but there exist these univariate polynomials E and these constants alpha i's and beta i's, such that this is an identity. So this product is ED of U1 times ED of U2 times ED of U3. So this is a product of univariate polynomials in the different UIs. So it's the same polynomial, but it's not important that it's the same polynomial. But it turns out to be the same polynomial. Yeah?
Here's the answer. I was going to say, if you're just saying it's a univariate polynomial, what's the point of alpha I? You can put that in the polynomial.
Right, good. So hence there was more notation than there was necessary. That's what I meant. You can just talk about EDI.
So one should note that the duality here is that there was sum of n variables and product of d of them, and it turned out to be a product of n things. So somehow.
So here is,
You replace sum and
let me just
product,
put this
something
back.
we are not supposed to do. With ends and ors, we have duality, so we can replace them. This in some form is exchanging
Right, in
the
some
sum and
form.
the product.
So here also there's a, so it's not, so here's a product of d things. Yes. So the main thing here, main gain out here is the fact that these things became variable disjoint. This was a way of just separating the variables out, in some sense.
But here you lose homogeneity, that
Yeah,
you
but
get
this-
a product which is huge and will be huge in our
Yeah,
application.
so exactly. So this is exactly the spot where you lose homogeneity. This was a polynomial of degree d. This is going to be a polynomial of degree m times whatever the degree here was. But when we apply it, m is going to be 2 to the root d. So these univariate polynomials are not going to be homogeneous. So this is the place where the degree completely gets out of control. So yeah, in this step you're going to pay for the degree, but the gain is going to be this variable disjointness. When you see these circuits, sum of product of, it's not obvious why I should replace these powers with these things, because this is a product of sums. This part is already a product of sums, and I'm just adding more complexity and I'm blowing up the degree. It's not, at least to me, it was not obvious that even if you knew this identity and you saw a circuit like that, it's to make the connection that, or to know that now, you can't see that if you plug that into that, then you get a depth 3 circuit out of it. Right? So I think so, but so maybe when we come to it, we'll do that. If you just take this identity and replace both those powering gates with this.
If you use this as an exercise, it's
Right. I mean, you need to know that it's going to work to try it out. It's not obvious. So you plug this in there, and you do it once again there, and then you just look at it, and it's all going to simplify out. And so one reason why it all simplifies out is if you have a univariate polynomial, then it can be, then if over in the algebraic closure of reals over complexes, it factorizes completely. So polynomial of higher degree can all become linear forms. So when we plug it in, all these univariate polynomials can completely get factorized out, and you can get a lot of products out of it. So that will be used to make it depth 3, but it's still not obvious. But we can do this part of it, and you have to plug it in to see that it actually works.
So the place where you use the fact that it's rational is only to argue that everything cancels out and you get depth 3.
No, both identities hold only over large. You need, for the first one, you need a very large field, like Fisher identity. Also for this, you need that.
Yeah, so for this, you need a large field because of all these alpha i's and beta i's. Are going to be, we need lots of distinct alpha i's and beta i's in the field for this step to hold. So hence the field size needs to be large enough here. The characteristic needs to be large enough for Fisher's identity to hold. So we can just see all steps. So now I've mentioned what these steps are. In themselves, they were all by themselves used separately in different places, and this is the paper is just piecing it together cleverly. It just comes together.
The field we're looking at is still finite. So it's algebraic because is it still finite?
Then we come with the rational numbers.
Oh, I see.
Everything I'm going to talk about is over the rational numbers. It will work over a large enough finite field because most of the arguments will go through. But it's cleanest to think over the rationals right now. So these constants in Saxena's trick, these alpha i's, and so okay, I'm going ahead of myself. But once you do this duality trick and come to this point, your circuit might have complex numbers as coefficients. Because I said that univariate polynomials can be completely factorized, and that's how you reduce the depth to depth 3. But when you factorize univariate polynomials, you will get complex coefficients. So this might be a circuit over the complex numbers. But then they also show that if you have any depth 3 circuit over the complex numbers, which computes a polynomial which is in the rationals, then you can transform it to a circuit over the rationals, which computes a polynomial over the rationals. So it never helps to go to, so any circuit over the complexes can always be changed to one over the rationals. It doesn't help to have complex numbers. So there will be a size blow up, but if So the size blow up will depend on the algebraic degree of those coefficients you're going to use in the complex circuit. So to go from complexes to reals, for instance, since I is the only thing of degree 2, the transformation is really easy. So there's almost no blow up. But if you have things of, if you want to go to the rationals and you have things of large algebraic degree, then you might have to blow it up. But the factor of blow up is just this degree. Okay, so should I assume the depth force, or also each piece itself is, so let me start with assuming the first reduction to a depth force circuit of the following form. If we have time and everyone's interested, I can say how that gets done. Okay, so let's assume we have a depth force circuit of the following kind. Let me even just state Fisher's identity, because once you state it, if it's true, it must be really easy to prove, and it is easy to prove. So I'll state that, and then let's focus on the duality trick first, because that's most interesting. Okay, let's do it. So the form of the identity I'm writing up here is what I took from Amir's paper, because I thought it looked a little bit cleaner, but we can attribute it to Fisher. So here is the lemma. So they exist. Let me not even say it like that. So let's look at product xi, I going from 1 to d. Then this can be written as minus 1 to the d divided by d factorial sum over all subsets t Okay, so the product of xi's is some constant times a sum of these linear forms to the power d. And the linear forms you take are just subsets of these xi's. You take all possible subsets of the xi's, sum them, take their dth power, and there's some plus minus sign.
Everybody would believe you if you just did the t equals 2 case. It's just x times y is simply x plus y squared minus x squared minus y squared. Everything is divided by 2.
So you just so even to prove this here, it's you see that the only monomial appearing here is this product of xi. If you look at how product of x1 through xd appears here, you will see that it exactly appears d factorial times here, which cancels out with d factorial there. So it appears once here, and all other monomials will just cancel out because these alternating signs will just cancel everything out. So it's some inclusion exclusion type statement, and it's not. It's just expanded out, and you can just check that all monomials cancel out. This is also this inequality, hence, because of this d factorial sitting here, it only makes sense over fields of large enough characteristic. So this is where the characteristic. So if the characteristic is larger than d, then everything works out. But here we are dividing by this d factorial, so that's what forces the characteristic to be small, to be large. Right. So that's the Fisher's inequality. So let's take this identity and plug it into these depth 4 circuits and see what we get.
The most general form, you can have more generalizations of this.
Maybe.
What?
It looks like, you know, like you can always have this, every non-linear polynomial you can, every field you can write in some sort of a Taylor expression, something like this.
It does give you, once you have it for monomial, you get it for every polynomial. Just
Right, so we can just replace x2 with x1 in this whole thing, and I mean, so you can just do, yeah, whatever, you can do any transformations to these xi's and just, it will carry over here. And so every monomial in every, in particular this gives you a gadget to replace every product gate. So every product gate in the circuit which takes in certain inputs, you can take those inputs, put it in to the xi's here, and you can write it as a sum of powers. So let's do that now to all the product gates in the circuit.
And the sum of powers is always of the same thing. Is that important? I mean, that it's always sums of variables that you.
So it was not important. So in this entire reduction, all that mattered was it's a sum of powers of linear forms. And what these linear forms were is unimportant. Yeah?
What is this in smaller size?
Smaller size, oh, less than 2 to the d?
No, it's a low one.
Yeah. So I don't know how to show that.
Maybe I don't know if 2 to the d is exactly the low one, but that is the easy exponential low one. Yeah.
So I think you can do 2 to the d minus 1 at least, but I don't know about anything better than that. What was I saying? Yeah, so in this entire, so when they, in this reduction, when they're going to use this inequality, d is going to be actually root d, because all those product gates have fan in root d. So each time you're going to have a blow up only of, so you're going to blow up this expression by a factor of 2 to the square root d. But 2 to the square root d, we're having so many factors of 2 to the square root d around that it won't matter. Okay. So let me state the lemma which results from plugging this into that statement. Okay, so here's, so let f be I don't know how. Yes, suppose you had a polynomial which is computed by some depth 4 circuit, where the fan in here is A and the fan in there is B. And the size of the circuit is, say, S1. Okay, then there is a homogeneous, so you get fan in A and B. Okay, so this is what you get by both these power gates will plug in, both the product gates will plug in to get power gates. The fan in of the sum gates will blow up because you're going to get these huge blow ups in the fan in of the sum gates. So the size blows up by a bit. So computing f, n of size, it becomes S1 cube a n of 2 to the a plus b. So if the degree here was b, you got a blow up of 2 to the b at the sum gate here, and if the degree a is here at this part, you got a blow up of degree 2 to the a. So it gives you 2 to the a plus b blow up. So it's basically the new size is polynomial in the old size times 2 to the a plus b. But a and b are going to be root d, and so this is going to be times something like 2 to the root d, which doesn't matter. I'll tell you why the cube, why you get more factors of S1. Okay. So you started from this circuit. So this part will be something like S1 times 2 to the b, right? Because this entire sum, this sum gate, if the original circuit had size S1, in particular this part has size S1. Yeah. So you get S1 and then you blew it up by 2 to the b. Okay. Yeah. Right? Now you get another S1 from this part. It will, so you just plug
So So that came from like the number of layers.
Came from the size of each layer, and then each monomial here, potentially there could be these at the second layer, these xi's at this layer, these xi's are going to be circuits of this form. Right? So each xi itself is going to be a big circuit. I'm going to replace the xi's by these big circuits. And so when I express it as this big sum, each xi will keep showing up as this big sum over and over again. So you will just get this circuit. So you just believe me that this is true, right? You just plug it in, just keep replacing product gates by sum gates, and this is exactly what you get. Just pure plug-in. So there's nothing surprising here. Okay, so you started with the circuit, made it depth 4. From depth 4, you just replace the product gates by these powering gates using Fisher's identity. Now let's see. But once you have these powering gates, first let's prove what Saxena is, that identity, this duality trick, that you can replace any linear form to the power d by a sum of products of variable disjoint things. Okay, so let's prove that, and then we'll plug it in and see if it does give a depth 3 circuit. Okay, so let me again state this lemma formally. Okay, so for every constants m and d greater than 0, and for all, let's choose alpha 1, alpha 2, so all constants for all alpha 1 through alpha md plus 1, there exist these constants beta 1 through beta md plus 1 such that that identity holds. Okay, so and this fact that it holds for all alphas, there exist betas, actually gets used later on when they convert a circuit over complexes to a circuit over rationals, and so it's important that you can do this. Not for some alphas and betas, but for all alpha, there exists beta for which you can do this. It's sort of important. So as I said, so u1 plus u2 alpha I. Right. So you'll be using the same alpha for different uj's, and then multiply it out, and then take the sum over different alphas. And this polynomial, so ed of u is just so you look at the Taylor expansion of e to the u and just cut it off so just go up to degree d. That's the univariate polynomial. So this is fixed univariate polynomial. You know what it is, and you're looking at the univariate polynomial of evaluated at different scalings of u.
You are using the same polynomials in the base, not quite the same, I think.
It's looking at e to the
Yeah, you truncate
e to the function times z and look at the coefficient of
that's right,
d.
but it's not quite the same, I think. Maybe it's identical, maybe it's equivalent, but it's not.
This is a Taylor expansion of what function?
E to the u is,
Oh,
yeah.
okay.
And so a priori it's not even obvious, it's not at all obvious that there exist such polynomials at all for which you can write this sum as such a product. right? It's not obviously exist. Maybe they exist, but maybe you have to blow up this sum by a lot. So I'm not sure. So it's not obviously exist, but they do exist. Now they do exist for these polynomials, and that's the setting. And yeah, the one thing to note is that here the degree did blow up. If m is much bigger than d, which it will be when we apply it, you got polynomials of much higher degree than what you started out with. So I'm erasing this picture because you know it. And let's prove this. So the proof is actually quite short. So we'll use the fact that this is the Taylor expansion of E to see why this gives it. Okay, so here is the proof. Okay, so let's give this linear form the name L. Okay, and let's look at the Taylor of expansion. Let's introduce this variable z and look at the formal Taylor series expansion of E to the LZ. Okay, so this is 1 plus LZ divided by 1 factorial plus right. So that's how it looks. And what we want to compute is L to the D. Right? So L to the D is basically the coefficient of Z to the D in this Taylor series expansion. So we want to be able to extract out the coefficient of Z to the D. So L to the D, observe, is D factorial times the coefficient of Z to the D right. Okay, but so here now we can see if you look at E to the LZ, this is the same as E to the U1Z times E to the U2Z times U. Right? So this is where this separation of variables is going to occur. You had this linear form depending on of d variables. You can by doing this exponentiation trick, you can break up and separate out the variables. Okay, so this is d factorial times the coefficient of Z to the D in this polynomial, in this expression. Okay, but now if we look at all these power series, the power series expansion of E to the U1Z, E to the U2Z, etc., notice that if you want to just get the coefficient of Z to the D out, you don't need to look at the entire power series expansion. If you just cut off the power series at a certain point at D, then this quantity is still the same, doesn't change. So this equals d factorial times coefficient of Z to the D in, and now cutting off the power series expansion is just like looking at this polynomial. So it's E sub D of U1Z times E sub D and now you just do interpolation. So you want to recover L to the D. So what you want to do is basically get the coefficient of Z to the D in this expression. Okay, but now let's just think of these U1 through UMs as constants or given to us, and let's view this as a univariate polynomial in Z. We want to recover some coefficient of this univariate polynomial, but a coefficient of a univariate polynomial can be just recovered by taking a linear combination of evaluations of that polynomial at a bunch of points. Right, so we can just and the evaluations we will take are precisely these points alpha 1 through alpha m. So what we'll do is just take this polynomial, evaluate it at alpha 1 through alpha m, take some linear combination, and that will give you L to the d. And that's exactly this expression. You've taken this product, you're evaluating it at alpha 1, and you're evaluating it at alpha 2, and at a whole bunch of different points. And these beta i's are the linear combination you will take to give you that expression. Okay, so for any set of evaluation points, you can always interpolate back.
The beta i's will be the entries in the
Inverse of the Van der Monde matrix corresponding. So you can choose alpha i's that you can look at the matrix is just solving a linear system of equations, and the beta i's will be the inverse. So then the magnitudes of the coefficients might blow up there potentially.
This e to the LZ thing, we're not actually looking at e to the LZ, we're looking at only the first d.
Right. So, right.
Okay, yeah.
So we're just cutting. It is the same as the coefficient of z to the d in this entire expansion, but that's the same as cutting it off at d because the higher powers of d don't matter. And hence what you want is exactly this quantity. Okay, so and so just by interpolation.
This is a very useful trick, and what means the variant that we use is actually for fast computation of symmetric polynomials in small depth, depth 4 and depth 6. So
Use this to reduce the depth from 6 to 5 or something?
we have two different upper bounds on which are sort of better than actually there you're trying to compute symmetric polynomials much faster than you can. It takes n squared, so it's well, you know, if you compute symmetric polynomials by arithmetic circuits over large enough fields, so the famous Ben-O result is that in depth 3 you can do it inside n squared, every symmetric polynomial. So in contrast to Boolean circuits where we have to pay exponential size, this is where arithmetic circuits somehow are more powerful, or big fields are more powerful because of interpolation. If you are unhappy with n squared size, n squared is the same the outcome. The question is what can you do for symmetric polynomials of low degree? And it turns out that using this trick you can get things that are better than n times to the root d and for that n times polylog. So you get much better profile. The proof of this exponential association is the same proof as the field thermodynamics.
So both, right? So both, that means both this Fisher's inequality and both these things were known together at the same time. But okay, they're not even different works, and the same work. Right.
Shubhangi, for the rest of the argument, we don't really care about what the form of the beta is.
We don't care about what these beta i's, alpha i's are right now. Right, so at least if you just want to get it down to a circuit over the complex numbers, and then it doesn't matter what the alpha i's are, what the beta i's are. It doesn't even matter what those univariate polynomials are exactly this polynomial. The just product of univariate polynomials is what matters. Yeah?
Here you need the field to be large, but is it sufficient that you also need, is it the case that you also need the characteristic to be large for the Taylor expansion of all?
So d, more than d? See, this still it's a d factorial. It's still d, so it's all okay. Yeah.
The characteristic has to be bigger than d, and the size has to be bigger than 2 to the root d, or whatever. Or here you call d squared d.
It's still d, or d or square root d or whatever. It's not exponential, but the field size will need to be when we apply. So I erased something maybe, but when we're going to apply this Saxena thing to the thing twice for both the power gates, and for the second power gate, m is going to be 2 to the root d. So we will need, and so we'll need the number of alpha i's will need to be at least 2 to the root d.
Field size doesn't really enter into arithmetic circuits. You take the algebraic code, you can always assume you're working in algebraic code.
To put coefficients in the field. So Grigoriev-Karpinski, for instance, works when you're not allowed to.
Yeah, but it's not arithmetic circuit.
Right. Right. So if you're allowing the model where you're allowed to put things from the closure, then the field size is not important. If you're not allowing that, then you need it to be large enough.
You can simulate exponentially large field using polynomial time, right?
Mm-hmm. Yeah.
Compute it over a small
Yeah.
field, you can still compute it.
Yeah. Okay, so let's now just take this and plug it into to the depth 5 circuits we have and see where the depth reduction comes from. Okay, so what we have is this sum product sum circuit of these the powering gates have degrees a and b, where a and b we are going to set to be roughly square root d. So we start with this circuit. So any such circuit, so let's look at what this polynomial looks like more explicitly. So it's going to look at like, so it's going to compute a polynomial of the form. So let's not even have sum gates. Let's going to look at T1 plus T2 plus. So suppose you knew that the size here was this quantity S2. You go up to TS2. Okay. So you have a sum of S2 things at most, when each Ti is a power sum circuit. Okay, so each Ti is of the following form. So it's going to be a power something to the power a, right? So something to the power a. The something what goes inside is a sum of power of sum. So it looks like Li1 to the b where these, you take linear functions, you raise them to the power b, you have S2 many of them at most because the size of the circuit is S2, and you take the sum. Right? Good. So now let's apply. So let's, this sum gate on top we don't care because we want to reduce it to a sum product sum. So this sum gate on top can remain a sum gate. Let's look at these now. Let's just take these Ti's, and if you can replace each Ti as a sum product sum, then we'll be done. Okay, so let's focus on any particular Ti and look at its form. It's lot of things summed up, and then you take a power. So you can plug in that identity out here and see what you get. Okay, and the UIs will be replaced by these powers of linear forms. Okay, so let's focus on any one particular t. So let me get rid of these extra coefficients for now. Okay, so you know that hence t can also be written as this big sum. The sum is up from I going from 1 to md plus 1, right? So m is S2, d is a. So I going from 1 times S2a plus 1 times the product. Okay, there are these beta i's also. Let's put them in. And there is this big product of j going from 1 to S2 of these univariate polynomials, but these univariate polynomials will take in these as the variables, these Li to the b's as the variables. So E sub a alpha I Lj to the b. So it's exactly that expression, but all the ui's have been replaced by these lj's to the b. Good. So now we got a sum of these products. Now let's focus on any one expression of this kind. Let's look at these terms. So you each term out here is a univariate polynomial which takes as argument lj to the b, right? Which is the same as some other univariate polynomial taking as argument lj. Right? So this is a univariate polynomial in lj, so it can be factorized into linear factors in lj, which are linear forms. So each expression of this is just a product of linear forms, and that's it.
Why again?
Okay, so now let's look at and this expression. We have these expressions e sub a of alpha I times lj to the b, right? This expression is basically some polynomial. Some polynomial of lj. It's a univariate polynomial in lj.
You have the b's root of alpha I.
Over the complex numbers. Right now this is just a right now this is without any bth root of anything. Yeah, maybe maybe here over the complexes. We are working over the complexes right now.
The alpha inside, you have to take this root. But it's over
No, you don't have to do that. Right, right. It's just a coefficient. Right, right. You don't need at the moment you're not.
Okay, I see.
So this is a polynomial in lj. Let's treat lj as a variable by itself. This any univariate polynomial can completely factorize into linear factors. So this looks like the product of lj minus some gamma ij, I going from 1 to whatever the degree of this polynomial is. Right? Then the degree is a times b. Right? Because a was the degree of these e sub a's, and you blew up and you got another factor of b because you had powers. So each expression here can be factorized into linear factors. So this looks like a product of sums. So you bring it back here, it's a sum of products of sums. So you got your depth 3 circuit.
Maybe I totally missed something. You replaced every power with some product sum?
No.
Oh, sum of power. You replaced some power with some product sum.
I just no. So what I did was let's write it out. I have this circuit.
Yeah.
It looks like this form. It's T1 plus T2 up to TS2.
The depth 5 circuit?
The depth 5 circuit looks like this. It's sum, power, sum, power, sum. So there's a sum,
Yeah.
and the sum, the things in the sum look like power, sum, power, sum. So they look like this. So I've not done anything. I've just explicitly written it out.
You're replacing powers of linear things you're applying them only on the top level of powering gates.
I just realized, yeah, you don't do it.
Only on the first layer.
That is right. You only do it once. That's a
Not
good.
even more.
So here we just use it to factorize. Here the power, yeah, that's a good point. We just use it once. We just use it on this gate.
On the top one, the other one, you just eliminate the exponent because the universe polynomial in a power.
That's true. So you don't use it twice. Yeah. You just so now you wrote it out. So this is just explicitly what the depth 5 circuit looks like. Only the top power you replace by a sum of by that identity, and now just observe that it all factorizes out into a depth 3 circuit. But let's see what the degree of this depth 3 circuit is. Right? The degree of these factors are going to be S2 times A times B, I think. Right? But when you apply it, S2 is already 2 to the square root D. So Whereas here the degrees might have been quite small. The degree blows up. Okay, so that's basically the.
Oh, I see. So in formal operations, you replace sum, power sum with sum product.
Yeah, but it's a product of things that are disjoint.
Yeah, it's not just sum product. It's sum product sum actually, because a univariate polynomial. So there is a sum sitting. If you just look at it abstractly.
When you polynomial you factorize, so it's sum product, right? So that's
You factorize, but it's
Yeah,
still
that's
sum
why
product
it's
sum.
product, it's sum
so it's sum
product.
product. So power sum became sum product,
Yeah.
and product and power mix and become power.
No.
Become
If you do
product.
no. So I think if you just do it at this,
It's not a syntactic thing.
it's not. You can't do it. The point is you can't do it syntactic. You can't take half of it, replace it to another by another circuit, and then put it in.
No. So if you
Thinking about just
incorporate
saying
the
what you
factorization,
wrote in.
if you just incorporate the factorization also into the duality.
No, but if you factorize it here and then plug this in, it won't do. You have to plug this part in and then factorize it. So it's not right. Right.
All these powers of linear things at the bottom there, and you need to separate them. You don't want to have sums of them. You just want to have univariate polynomials in just one of them, and then multiply them together. That's the only reason you can factor.
So somehow it's not syntactic, which is what I was saying in the beginning, that if you knew the duality trick and you knew this identity, there's no syntactic way of viewing this reduction without actually looking at the explicit form, plugging it in. I don't know any intermediate form where you can simplify this by a product sum and then something happens.
Then it brings the question whether this is the simplest way of doing it now that we know the result is correct. Maybe
Right.
there is a more direct interpolation idea. When you take any depth for sigma pi, the product degrees are small. What's the interpolation trick? Probably there is a more direct way of doing it.
Yeah, so that now you plug in the values, it just everything works out just fine. So you get your depth 3 circuit. So yeah.
So you get this product on the bottom here, and this is also linear because it's a linear minus constant.
Right. I can say a little bit about why. So when you do this factorization, at this point you've gotten in all the complex numbers into the circuit, because you started with the univariate polynomial E sub a and you factorized it. Right, so at the moment the circuit has complex coefficients. So let me hint at why you can get rid of the complex coefficients and you can make it a circuit over the reals or even the rationals. So let me state the lemma which they use and prove. So here's a lemma. And this lemma basically is a way of taking any circuit over a field extension and converting it to a circuit over the base field. So suppose you have a polynomial f. This is capital X, so this is an n tuple of variables in suppose this is computed. Suppose it's computed by some product sum circuit of top fan in and the formal degree is d of the polynomial is being computed. So not the degree of the output polynomial, but the degrees of all the intermediate gates combined. Suppose you have such a circuit, and suppose the coefficients come from some extension field with some finite extension of K mod Q. You see, you have polynomial over rationals, but the circuit has coefficients coming from this field extension. Then the claim is that you can have a circuit, then you can replace this circuit with a circuit purely over the rationals, but then the size blows up by a little bit. My book went in. So there is an equivalent sum product sum circuit of size. So it's some polynomial in the original size, the formal degree of the polynomial, and the degree of this extension. And now the coefficients are in Q.
And the degree of this extension will be the degree of the polynomials you are factoring.
Yes. It will be, no, you look at all the polynomials you're factoring and the, right. So what's lucky is that the polynomials you're factoring are the same polynomials. For all these E sub D's are the same. Because otherwise you would have to take the roots of all these polynomials that join all of them and the degree might have blown up. But luckily the degree doesn't blow up because it's all the same polynomial.
Why? I mean, even if you take all, even if it were different polynomials, it would still be, I mean, it would still be a polynomial number of roots, right?
No. So each root, each root has degree. These polynomials have degree m, but where m is 2 to the root d.
Oh,
But polynomial and 2 to the root d is still
No.
2 to the root
The
It's-
polynomials don't.
They must.
No, the polynomials have just degree d. The polynomials have degree d. You multiply m of them, but the polynomials have degree
No,
d.
but you plug in some power into it also. What power is it?
It's b, so together it's degree ab, the polynomials. Those you are factorize. The problem is you have many of them.
Yeah. So good.
Yeah.
You might have 2 to the root d many polynomials. The total number of polynomials you have here is 2 to the root d.
okay.
So
So the degree of the extension will be 2 to the root
No.
d times.
It will
When
no.
you add the-
If you multiply them, so you'll have d times d times d times d, 2 to the root d times.
degree
That's
of
the degree of the extension.
Is the product of the degrees of each extension.
Oh, right.
So hence it would really blow up. But luckily now they're all the same polynomial. So you just need to join the roots of one polynomial. So the degree of the extension is small. So this entire thing would work out. There's another place where you need also the roots, the 1 over bth roots of these alpha i's when you do this factorization. But you can these alpha i's are your control, so you can choose them to be bth powers right from the beginning. So that doesn't play into the degree of the extension. So overall, the degree of the extension is going to be small.
So this is standard, but not for depth 3, right? So for depth 3, you need to make sure that it works.
I suppose it's standard. I don't know
There
it is
won't be,
standard.
I mean, just,
Yeah, so you just so
you take a basis for the extension and you work over the basis.
right. So this is quite simple.
But
So-
you just have to make sure that even for depth 3 it works.
You have to make sure for depth 3 it works, and it turns out to be another case of polynomial interpolation. Just like the proof of Saxena's duality trick, it's going to boil down to. So let's just see. So maybe it's just the toy case. Let's see how you can convert complexes to reals with and it working in depth 3. and that will give a hint for the general case instead of doing the whole general case. So let's let's just convert it to the real numbers just for now. Good. So we have, let's do a proof, and just to go from complexes to the real numbers. Okay, so suppose you have a circuit over the complex numbers computing a real polynomial, a depth 3 circuit. Let's convert it to a circuit over the reals. Okay, so you have a sigma pi sigma circuit. Okay, so it's a sum of products of sums. So let's focus on any product of sums and fix this, make this reals, and that would be enough. So let's look at.
But you'll make it into a sum product sum.
We'll make it into some product sum. So let's look at some product, a product of linear forms. Li, good. I going from 1 to d. Let's just focus on any such expression.
Isn't it just that you need to compute the symmetric polynomials?
It's almost symmetric, but it's not quite symmetric. So let's write it out. So each linear, so each Lj can be written as Lj. You can just replace it with Lj plus I times Lj prime. That's L is a bad. So some linear form which there is a real linear form plus I times the complex variant of it. Okay, so this is, so you get G1 plus I G1 prime times G2 plus I G2 prime times GD G, right? And what we want out of this is the real part. Right? We don't care about the stuff which when you expand this out, it will look like something plus I times something. The coefficient of I we don't care about because it will never contribute to the real polynomial in any meaningful way. So you're only looking for all those terms where an even number of i's occur when you expand this entire thing out. So let's do it piece by piece. Let's look at the term where only the 0 i's occur. Let's look at the terms where 2 i's occur, the terms where 4 i's occur, and so on and so forth. And we want to recover those. Okay, so when 0 i's occur, it's just G1 times G2 times GD. That's easy. That's already a depth 3 circuit because you know these G1 through GD.
So you're going to treat I as X.
So yes, what we're going to do is, so now what we do is let's treat I as X. Let's replace I by a formal variable X, and we want to know the quotient of X square, the quotient of X to the 4th, X to the 6th, and so on and so forth. And each coefficient of, if you have a univariate polynomial, the coefficients are linear forms are linear combinations of evaluations, right? And the evaluations are a depth 3 circuit anyways, because you just plug in. You already have this expression. You just replace I with X, so you have a depth 3 circuit. So all evaluations are depth 3 circuits. So linear combinations of evaluations are also depth 3 circuits. So you can compute all these coefficients of I to the I square, I to the 4th, and so on and so forth, and just sum them up. Right? So that's what you did with I. You can do in general. If you have some other field extension, you find a basis for it. You would write each. You can replace each linear combination, each linear form as a linear combination of the basis elements, and do exactly this thing more carefully. And the blow up won't be too much.
And you have to do mod X to the mod defining
Right.
polynomial.
Right.
So it's not like the success, it's like the original Benovo.
It's like,
Interpolation.
right. Only the yeah.
Yeah, but when you have maybe an extension of size 3 or more, then it's something slightly trickier, right? Because then you're taking more.
So this was a simpler case. It does get a little bit more tricky. Yeah.
Is it enough to say that you can do it on the base field using a
But again, you might get complexes once again.
Do we know of any case where having a gigantic field extension actually gives you a very significant savings in circuit size?
Yeah, so exactly this, if you, I don't know what you mean by gigantic, but if you want to compute a symmetric polynomial over a fixed finite field, then this is like, let's say over GF2, then this requires exponential size. But if you want to do it over a field with n elements, then you can do interpolation. And this size n squared. So the field size matters just in order to get lots of different constants. That's the only source of help I know of for saving in size.
For the reals to complexes, you don't trouble. For the rationals.
Really
Yeah.
complexes, I don't know such.
And in fact, this proves that.
But for rationals, but if you can have from rationals to complexes, it could still be very big.
With similar example, if you look at PITs, so PITs and low bounds are related. If you allow like very, very, very high field extension, you can just evaluate the circuit at one point and get the answer, but this is like cheating. If you allow like very, very, very high extension.
No, but then the coefficients also of the polynomial also come from a very, very high extension. So then so it's not cheating, but
In the sense it is cheating.
in fact, no, then it doesn't work.
All right, thanks.
Okay. Yeah.
Questions?
If you just use this lemma,
What lemmas?
if you just use this lemma about converting products to powers,
This Fisher's thing.
on
Yeah.
the fourth circuit,
Yeah.
the top level, you get that every circuit can be written as sum of powers of sparse polynomials.
Yeah.
For homogeneous, in homogeneous models. So is this something might be easier to apply the shifted partial derivatives to, or it's like the same depth for reduction, just that in any product it's the same polynomial and it's sparse.
That's a good question. I don't know. It's definitely worth looking at.
Might simplify it, or at least it might give some better, something better.
No, but it's also low degree. Oh,
I just suppose you apply the original lower bound.
Oh, if you just apply to the top, at the bottom level or the top level you're applying?
Top level.
Top level is, but then you the blow up is going to be pretty. It's fine, right?
It's the
Whatever.
same blow up.
It's the same blow up, right?
blow up. That's what
Is a product
Right,
of
right,
square root and
right,
sparse polynomials, and
right.
each linear combination of them is also sparse.
It may just simplify some of the binomial coefficients
Right,
in
but
the
it
value.
wouldn't improve them.
Yeah,
because you
no,
use
it
the same
cannot
one.
improve
Yeah.
because the determinant is like.
Maybe a different measure that's low for powers of sparse.
It's interesting, yeah. So one thing, so one observation they make is that okay, they went from these depth 5 powering circuits down to the depth 3 circuits, and then the blow up happened in going from these depth 5 to the depth 3. So it's not clear that whether you simplified life from going from depth 5 to depth 3. Maybe those depth 5 circuits are the better circuits to study than going down to depth 3. So just lower bounds for those circuits are already.
Blow up from 4 to 5 is also exponential.
The degree never blew up. For depth 4 to depth 5, the degree stayed the same. It still remains homogeneous. The depth 5 is still homogeneous. Yeah, yeah. The size blew.
But they say, well, you can do it for both.
Yeah, do it for or just for one. Yeah, even for one or for two, even if you do it, it still remains homogeneous, that step. And maybe that's a better circuit to start asking for lower bounds than the depth 3 circuits. They also show in the paper a reduction the other way. So here they started from depth 5 and went down to depth 3. But you can also start from depth 3 and get blow it up into a depth 5 powering circuit by some exponential loss. So there's a connection both ways.
Isn't depth 3 also depth 4?
No, depth 5 with powering gates, no product.
Yeah, but the depth
Oh, but the degrees are, maybe the degree is what's important.
No, but you don't lose from depth 4 to 5 with powering, you don't lose the degree.
But depth 3,
Depth 3 is also depth 4.
so maybe it makes sense if you have a depth 3 circuit computing a polynomial of small degree, then you can blow it up into that might be the statement. Even if the depth 3 circuit itself had really large degrees, as long as the polynomial it was computing has small degree, then maybe the depth 5 circuit.
Just look at it as an arbitrary circuit and do the whole thing from scratch.
Mm,
But then you lose this. I mean, why is what they're doing better than that?
I don't know. I think this part of the paper I didn't look at very carefully. So I can tell you the formal statement. Let me tell you what the formal statement is. Okay, let f be an n-variate polynomial of degree n, okay, over any characteristic, computed by a depth 3 circuit, top fan in S, product gates with fan in at most D, okay. Then there exists an equivalent powering circuit. So maybe those parameters, how it depends on NDS, is not what you get. But there's a 2 to the root n blow up. Yeah, I don't know what happens if you start from scratch. Homogenize it, start with the circuit, homogenize it, do everything. I'm not sure.
It seems to me that one thing to do immediately is to take just a product of multiplying, not determinant, multiplying d by d matrices and get a depth 3 size 2 to the root d circuit for it. And that should be somehow directly. Yeah, so in particular, well, we said that a consequence of the result is an upper bound, a depth 3 upper bound of 2 to the root d for determinant of d by d.
Right.
So in particular also for the product.
Right.
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 So it exists.
Right. What is it you mean?
What does it look like? This is a mess, you know. So I mean, it seems like this problem, it's probably you break it up to root d by root d matrices that work from them, but just somehow combine the, an outer level. And there's some essential use of interpolation as well.
So maybe much simpler way of doing this.
Much simpler way of doing it. And actually, if you do it for products of matrices, you do it for the whole thing because everything reduces to a product of matrices.
So they start with product of matrices anyways in this whole thing, yeah. Right.
Yeah, by the way, for those who never saw it, I mean, the result that Shubhangi did mention, I mean, that gets you from a circuit or a formula to a depth 4 circuit is extremely simple. Because any circuit or formula can be just written as a product of matrices. Let's say d by d matrix.
This is